Hi, grade 10s. So today we are moving on to chapter 5, and this is still our physics unit. It's just another section, and it is not really related to work or specific heat capacity that we've been dealing with at all. But we are still going to use that very first concept we learned about significant digits and scientific notation for our answers, which we always do, no matter what physics calculation we are going to be completing. Okay, so today we're learning about vectors and scalars. Okay, these are terms that you're going to continually hear if you take physics down the road. So what is a scalar and what is a vector? A scalar, okay, and vectors both involve numbers, but there's a distinguishing factor between the two of them. So a scalar simply describes magnitude, which is just the number alone, the amount, but they have no defined direction. Okay, so no direction. So south, west, east, right, left, up, down, that's direction. Where vectors are quantities, a number, that do include direction. Okay, so these would be two key terms to write down in your notes. You will have an assignment on these application questions. Okay, so what's a vector? What's a scalar for examples? So a vector, like I said, has the number or a quantity and direction, where a scalar is a number or a quantity, but it has no direction. Okay, so a classic one that's pretty easy for you guys to understand right off the bat is time. You're not going to go left, right, forwards, backwards in time. No, we're not time traveling. No, you can't go backwards in time. There is no direction to time. It is strictly just a number. Where, okay, if you were to look at, for example, acceleration is a vector. You can either accelerate extremely, some people say accelerate really fast, so that's a forward motion, but you can actually also decelerate, which you're slowing down extremely fast, which means you're actually going backwards with your acceleration. You can decrease it. So it is going to have a direction. Displacement has direction. So this would be like left, right, south, east, west, north. Distance is the exact same as displacement, but doesn't have that direction involved. Velocity, most of you guys interchange these two, speed and velocity. Say, I'm going 20 miles per hour. Okay, what direction though? Are you going north, south, east, west? As soon as you add direction, you're talking about velocity. You're just talking about a number. You're talking actually about speed. So these would be examples that I would put down. Examples of vectors, examples of scalars, but I'm going to actually come back to these too. Okay, so to differentiate between them, we use D to represent distance. Okay, in our work is equal to force times distance calculation, you noticed there's the change in, that's the delta symbol, and you'll notice it was just a plain simple D. Now, displacement, however, is actually indicated by the fact that it has an arrow on top. Okay, and this arrow is what tells us that it is a vector, and so therefore needs direction. Okay, so I couldn't get away with just saying 20 meters like I could over here. I would have to say 20 meters east. Okay, so we often use vectors. We represent them with arrows. Okay, The arrows represent magnitude in comparison to other arrows. It's not a precise measurement in this situation. 50 meters to the right, you'll notice the 50 meters is much larger than the 25 meters to the right. So it is relative in comparison. So you shouldn't be drawing, if I was to draw a vector, you couldn't tell me that this was 1 meter and this was also 0.5 meters. There's not even really a close comparison to it being about half. Okay, not a perfection thing, but it's an about for right now. So this arrow is indicating a vector because it's 50 meters and there's the direction to the right, 25 meters to the right. So there's a vector, but you'll notice this is 25 meters to the left and the arrow is pointing the other way, and that's to represent the direction. Okay, these are key terms you're going to see, and you need to know the difference between them all. So position is a vector quantity that describes a position relative to a reference point. This has a symbol of just a plain old D, and the units are in meters. Distance, units are also in meters, but this is a scalar quantity. Okay, it tells you how far something has actually traveled. So has it went 100 kilometers? Notice no direction involved. Displacement, vector, and the key part here, and I'm going to do some examples, is describes change in position. And you'll notice there's the vector symbol with the arrow on top, and the units are still in meters. There's nothing different about the units here for these three. Speed versus velocity. Okay, you have to distinguish between the two. Speed is a scalar, no direction. It describes the distance traveled in a certain time period. Velocity, still distance traveled in a time period, but it's a vector, so therefore it has direction, and that's indicated by the arrow on top. Notice units are the same. We almost always deal with meters per second for most of our physics calculations. Okay, so difference between position, distance, and displacement. What's the difference? So the best way is to look at an example. So let's say students at their locker in the hallway. The student's going to walk to a friend's locker, which is 15 meters south. Okay. They realize they forgot their calculator, and they have to go walk back to their locker 15 meters the other direction. Then, once they have their calculator, they're going to actually go to their classroom, which is 20 meters south of their original locker. Okay, so what is the distance walked by the student? Okay, so distance is the total, basically, surface that the student has covered. Has absolutely no impact by direction. So they went 15 meters south, but they've went 15 meters, so no direction involved. They went 15 meters the other way, and then they also went back to their classroom. So 15 plus 15 is 30 plus 20. So they have actually traveled a distance of 50 meters. Okay, no direction. What is the student's displacement? So this is where it has direction. Usually, for calculation reasons, I will give my directions in either a negative or a positive. So 15 meters south would be, well, usually south I think of kind of as backwards. So 15 meters, negative 15. Then they're going to travel 15 meters north. So the other way, so positive 15. And then they go another 20 meters south. So negative 20. So these guys, negative 15 plus 15, essentially cancel each other out. That's 0. So the displacement for the delta there traveled is actually negative 20 meters, which I prefer to always write a direction. This is just kind of my help for the math. 20 meters south. You'll see me write the square brackets with an S inside and another square bracket to represent the direction instead of writing the word south out. This is just a notation that is often used in physics. So here's displacement. It is the overall change in position, where distance is the total area that has been covered. Okay, so if you were to look at this little Pac-Man game, consider the difference between distance and displacement for the Pac-Man trip shown to the right. All right, so the distance is usually the easiest one because all you have to do is add the total up. So they have went 2 to the left, 3 up, 3 to the right, 1 up, 1 right, 1 up, and 4, and you should get 2, 3, 5, 8, 15. So they've traveled 15 spaces. Now this would be distance. Displacement includes direction. So how far have they traveled with direction? Now I'm actually going to look at this and say, okay, well, they've started here. And if I look at my stopping point, okay, how far have they went up and how far have they went over? So they have went 2 to the left, so negative 2. And then they went 3 to the right, so positive 3, or they did go up, but I'm going to look at just the lefts and rights for now. Then they went 1 to the right, and then they went 4 to the right. So negative 2 plus 3 is positive 1, positive 1. They've went 6 right. And direction-wise for what they've went upwards, they've went 3 up. So positive 3 plus 1 up plus 1 up. And that is it. So they've actually went 5 up. So their displacement is 3 right, 5 up. Because if you look, 5 up ends up being all the way up here. And then they've went 6 to the right. So they have actually traveled from their starting point to their ending point. And that little arrow right there, you'll see more in Physics 20, but is what we call a 2D vector is what I just drew there. So vectors often have, if they have 2 dimensions, we put them together using a tip to tail method. So where you start, okay, so let's say you went 3 meters up, but because it has 2 directions, then they went, or north, they went 4 meters east. So tip, there's the tail of the arrow, and then the tip tail, they join up, and then we connect. Okay, our starting point to our end point, okay, to give us what we call our resultant. And this represents our total displacement. You do not have to, at this point, use Pythagorean's theorem to calculate it. We don't do it in Science 10. It is a concept covered later on, but understanding how that vector is drawn is a nice key piece we cover in Science 10. So tip to tail, start, draw the arrow with slight magnitude comparison in the direction it's going. So this is north, which is why we're going up. East is to the right. So a little compass, just a little reminder, north, south, east, west. Okay. And then we take an arrow from the beginning of the first vector to the end, and that's our total displacement. So that is where I'm going to leave you for vectors and scalars. And we will be learning about velocity and speed calculations next. Hope you guys have a good day. Bye.